Welcome back to our live training session. In this training module, we're going to be taking a look at completing the base map creation process, setting up the two-dimensional and three-dimensional tables within our Motec programming, also taking a look at some other things like engine failsafe protection if we want to implement that, and also making sure that we don't have other motorsport features turned on so that we have everything stripped down and configured properly so that we can fire up the engine and run it in an alpha end strategy and at least have a reasonable starting point for beginning our control. So the first thing we have to do here is actually go in and take a look at our main volumetric efficiency table. In an alpha end strategy, we use the estimate table for actual calibrating and tuning, and what we'll find is that the volumetric efficiency table here has to be turned down to a singular one-dimensional cell point, and then that needs to be set to 100%. Let's do that first. Now, again, this is normally what you do for inlet manifold pressure speed density based tuning, but because we don't use an inlet manifold pressure when we're talking about true alpha end tuning, we need to go in and make sure this is not going to be called on, and we're going to be using just this estimate table for doing the alpha end strategy tuning. Let's go in and take a look at this. Let's go jump to field tuning. If we click A here, it's pretty simple to configure this table to suit an alpha end strategy. We'll toggle off engine speed, toggle off inlet manifold pressure, click OK. Now we're left with a singular cell point in the table. Now all we need to do is set this to 100%. Let's go here and type in the value, click enter. And we've saved that. I've stored that to the ITB K24 base file that we've created in that last tutorial. The next thing we need to consider here is our target lambda table, the desired lambda aim. We want to make sure that this is set with accurate desired target lambda values so that as we're varying the engine speed and varying the inlet manifold pressure, it's going to track to an appropriate target. Now, how do we do this? Well, if we go in here to the table, first off, this table is set to go to 8,000 RPM. RPM, it's fine in terms of our scaling and our breakpoints. But what I don't like is the inlet manifold pressure here is going all the way up to 300 kPa. Now, because we're alpha end strategy, we're actually not using an inlet manifold pressure sensor. It's going to be actually calculating and estimating this value coming from our estimate table. So what this is going to do is allow us to chop away in this naturally aspirated state 120 to 300 kPa. We're not going to have to worry about getting up into anything higher than 100 kPa manifold pressure because we're naturally aspirated. We're going to go here to delete or remove, and that's going to take that away. Now there is a driver fuel mixture aim switch that we want to turn off because that gives us the ability to have two different target aim tables. That's not really going to be relevant for this particular strategy here, so let's click OK. So now we're left with this table here. If we click F6, we can expand this out. That gives us the ability to map our desired fuel mixture aim or target lambda based on inlet manifold pressure, that's an estimated value, and then engine speed. What I'm going to do here is anything above, let's say 80 kPa, I'm going to set my desired target lambda to 86 lambda. That's a pretty good target for most any naturally aspirated engine. Then when I'm here from, let's say 40 or even 60 kPa and below, I'll say from up to about 3,500, we're going to set that at 1.0 lambda target. So this is going to allow me to run it stoichiometric. We want to get a little bit better economy. Now, when we're talking about alpha end strategy and doing tuning with individual throttle bodies, it's really a pure race kind of application. So economy isn't the first thing we care about, but we don't want to go in and just have be wasteful with fuel, especially if we have to keep track of our fuel consumption during lapping sessions. We don't want to have the values here at something like 86 lambda throughout the entire table. We want to be specific with this. Now, at 4,000 RPM and higher, I'll set this to something like, let's say 94 lambda in part throttle. We wanted a little bit richer mixture when we're at high engine speeds in our lighter vacuum ranges here. So this table is just pretty basic, just something that we have to configure and set up. So it's going to work here for our setup. Let's go into F6 and collapse that down. Now let's go to our startup fuel. Now in our startup fuel table, we have a couple different things to talk about. We have our cranking airflow, which is not going to be relevant. We don't have an idle control motor on our individual throttle bodies, so cranking airflow is doing nothing. There's cranking spark timing at 10 degrees, that should be okay. We have our cranking fuel. This is going to be looking at coolant temp versus crank engine cycles, how many times we're cranking an engine over. It'll vary the amount of fuel that we're going to deliver. Now we don't know if these values are valid or not, so we're just going to leave them alone right now and test and see how the engine responds. Some of the default Motec tables work okay out of the box and take minimal adjustments. So I'm not going to go guess what the values are going to be. We'll actually have to test it. The cranking spark here at something like 10 degrees might be a little bit too much. We might get some spark kickback. I'm going to set it to 5 degrees here in my value. And it looks like I was accidentally clicked on the target lambda table. Let's change that back to 1.0 lambda. Now we can get more specific with our cranking spark, and we can actually set this based on coolant temp, which might be a good strategy. So colder coolant temps, a lot of times we need higher cranking spark. Warm temps, we can usually back away the cranking spark. We don't need as much advance or as much torque output under cranking. So let's go here and set this to 20 Celsius increments. So 0 to 100 Celsius, 20 Celsius increments in the table. And we'll leave the table set on values of all of 5. Next thing to take a look at here is our post-start fueling. We can see some of the default values here, coolant temp, engine runtime. I'm going to say here by 30 seconds in, for sure, we're going to zero all this out. We don't need any post-start enrichment there. I'm also going to go here and just do a Control H and just vertically interpolate some of the values that they have populated because they're a little bit odd the way it's applying. Even doing H right here should be okay. We'll have to test and see how this is going to do in terms of firing it off and seeing if we need the post-start fueling on a warm engine here versus a cold engine. Warm-up enrichment will run with these values. We're likely to need more warm-up enrichment than we find in here. Again, we're going to test this out as we get into the cold start tuning and making sure that's all good. So we're not going to be able to do anything yet. Now the lambda ECT offset allows us to vary our desired target lambda from, let's say, cold idle from 1.0 lambda. We can actually override this at idle conditions and target a slightly richer mixture to get a little bit more engine torque and stability out of the engine when it's firing off cold. So if we take a look at the table here, I'm going to expand this out. We'll click A. I'll put a breakpoint here at 20 and then maybe even 30 Celsius and click OK here. Now once we get up to, taking a look at this, 0 to 20, we're going to set this at 90 lambda. This is going to bypass our 1.0 desired target lambda on a warm engine. Once we get up here to about 40 Celsius, we're going to make sure we set this to 2.0 lambda target. Motec's always going to use the richest of all the commanded target lambdas within the control. So by 40 Celsius, we're essentially going to go back here at idle to the normal 1.0 idle target that we find right there. Between 20 and 40, we'll do H. We'll just interpolate that. And it probably doesn't even matter here. Even at 30, we could probably command something like 90 lambda and allow it to go here as it's going up in temperature between 30 and 40 to kick right over to that normal target lambda here. Again, the value of 2 signifies that we don't want to run it and do anything with it. Okay, everything in here looks good. We have our transient tuning, and we do see the transient.
Thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here, and you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.